This video is going to focus on the mathematics behind the SIR model. So just to recap, the SIR model is a model in epidemiology where people begin in a susceptible population, eventually fall ill with the disease and move into the infected compartment, and then finally recover after some period of time and are granted lifelong immunity to the disease. And there may be people who begin also in the infected or recovered compartments. Okay, so in terms of movements or dynamics that are going on within this system, the change from susceptible to infection or to the infected compartment we can denote as alpha. Okay, and then the change the rate at which people are moving from the infected to the recovered, we can denote that with beta. Okay, just two letters. So in terms of overall movement within the system, again, nobody's dying necessarily in this system, but S, the susceptible population, is going to decrease by alpha. Okay, because people are moving out of that compartment. Recovered is going to increase by beta. Okay, so beta, people are only ever entering the recovered compartment. Now, the infected compartment has two dynamics going on. So people are entering and people are leaving. So since people are entering, that change is denoted by a positive value. So it's going to be positive alpha. So they're going to come in at a rate of alpha. And then they're going to leave at a rate of beta, so minus beta. Okay, but now we want to know what those values are specifically. So beta is going to be a little bit easier to compute, so we'll begin with that. Okay, so the value of beta is called the recovery rate, so the rate at which people are entering the recovered compartment is known as the recovery rate. And so again, everyone recovers from the disease eventually, but only a percent of the infected recover each day. So if we assume, or if we know that the infection lasts for K days, that means on average each day 1 out of K people are going to recover. Okay, and that value is called the recovery coefficient, which is just beta. So it is not beta. Each day, 1 out of K of the infected population recovers. So that means beta. Well, it says, well, some proportion of the infected population is going to recover, and that is going to be 1 out of K. Okay, so this 1 out of K is called the recovery coefficient, and it's the proportion of the infected. So it's the proportion of people that recover each day. Okay, so beta is rather easy to compute. If we know it lasts for K days, that means that the recovery coefficient is 1 over K, and then we can multiply that by the proportion, or by the number of people in the infected compartment to get the recovery rate of beta. Okay, now alpha is going to be a little bit more challenging, and alpha is called the transmission rate, so the rate at which people are falling ill with the disease. Now, transmission is going to vary jointly, so it's going to depend on the number of susceptible people and the number of infected people. Okay, so if it varies jointly, okay, that's a statement of variation, and I'm going to write this as A times S times I. Okay, so varying jointly means it's a product with the product of the two values that are specified with a constant of proportionality, which I'm going to call A, and that A happens to be called the transmission coefficient. Okay, now we can actually determine the value of that transmission coefficient through the following process. So the susceptible population has a certain percentage P of coming into contact with disease. Think of this as the probability of meeting an infected person. Okay, so you're out in public and not everybody that you're going to meet has the disease, but maybe say 10% of them do. So of the people that you come in contact with on this come in contact with on a daily basis, 10% of them might have the disease. Now, if you meet that person, okay, you're not guaranteed to fall ill with the disease, so you may or may not contract the disease. So if you make contact, then there's also a percentage Q that corresponds to your chance of actually contracting the disease. So this is the probability of contracting the disease if meeting an infected person. Okay, so in other words, if we want to know what that value of alpha, or the value of that transmission coefficient is, all that is A is equal to P times Q. Okay. Alright, so what that means to us is that alpha as a value, so alpha was equal to ASI, this is P times Q times S times I. Okay, and again, so P and Q are the percentages that we just talked about. S is the number of people in the susceptible compartment. I is the number of people in the infected compartment. Okay, so what that means is we can write those rates of those rate of change equations for the various compartments in the following way. We can write S prime, okay, we said it was minus ASI, that's also equal to negative P times Q times S times I, okay, and I prime, again, so I prime we wrote as ASI minus BI, so again this first one, S prime, that was just minus alpha. This one was alpha plus beta. Okay, so you can see, or sorry, minus beta. You can see each of those quantities represented here. And then lastly, the recovery, or the rate of change in the recovered population, that was just beta, which is BI. Okay, and so that is a brief explanation of how we get the mathematics behind the SIR model.